Welcome back to our AP Chemistry Kinetics notes. We left off last time talking about just the basics of a rate law, how the nature of the reactants had an effect, and how the concentration of the reactants has a big effect, and how we work that all out as a rate law. And what we're going to do in this lesson is figure out how do scientists actually calculate these sorts of things. So again, rate laws are determined by experiment. So here is some imaginary experiment data. Okay, this would be the kind of thing that we would set up. Initially, I would do 3 experiments, and initially I would have so much A, and I'd have so much B, and then I would measure the rate of C forming. And my equation up here to remind you is that A and 2B will yield C. Okay. So how do we begin? Well, we're going to isolate some effects. We're going to look at experiments 1 and 2 and ask ourselves the questions, what stays the same, what changes? Hopefully you see A stays the same while the concentration of B changes, specifically doubles. Okay? So, what is the result of doubling B? Again, A stayed the same, no change. B doubled. What's that result? Check out the rate of C forming has, be sure your exponents are the same. That's going to trip you up. Students get that messed up all the time, so be careful. We're going to have the rate 1.5 to 3.0 double. So how do we say this on the AP test? This is like the one case I'm very much so saying write it this way to be sure that you are very firmly getting your point across and not leaving any ambiguity. It's not difficult, but this is the kind of response they're looking for. First, you have to tell what experiments you were looking at. So I say very clearly, in experiments 1 and 2. Then I say what that tells me. I see A is held constant, and I see that B is doubled. Now I haven't said any results yet, I'm just saying what I'm comparing, but that leads them to understand what's going on in my head, and that's what they need to see. Then I tell them of what I observe happening to the rate, and the rate of formation of C doubles. And now I like to get all mathy. So here's our, it's on the former slide. The equation being rate equals K, concentration of A to X, concentration of B to Y. Okay, just a generic rate law coming from our equation having reactant A and B. If A stays the same, what number would represent the same? 1. If B doubles, what number represents doubling? 2. If the rate doubles, what represents doubling? 2. So now I ask myself, what exponent could y be such that a 1 times 2 to the y would equal 2? And of course, this really doesn't, we can simplify that way. Oh, look, 2 to the what equals 2? Well, please tell me 1. 2 raised to the exponent of 1 is 2. So therefore, y is 1. What do I know? And I like to say this again, even after saying, so y equals 1, I say, therefore, the reaction is first order with respect to B. That's the vocabulary you'd want to use in that case. First order with respect to, and then in this case, B. Okay, so now I know y. Check. I don't know that x yet, so we need to do it again. And I'm going to look at my chart and I'm going to pick appropriately. Let's look at experiments 1 and 3 now. What happens to A? Well, the exponents are the same, so A doubles. And what happens to B? B is staying the same, it's identical. And what is happening to the rate? Exponents match, so the rate is going up by 4. Ooh, that's interesting. Lots of fun, right? So here's what I would say. Between experiments 1 and 3, the the concentration of B is held constant and the concentration of A is doubled. Now, you could flip that. That makes no difference. You could say first A is doubled and B is held constant. They don't care. And I'm going to say the rate of formation of C increases by 4. And then I'm going to do my equation again. Again, our generic equation, rate equals K, concentration of A times concentration of B. Now, we've already found B was first order. If we want to, we could plug that in now. We're looking for what that X is. So A doubled, so there's my 2. B was held constant, there's my 1, and if you want to raise it to the exponent of 1, which we already discovered, that's fine. And I ask myself, and that simplifies away. Okay. So I ask myself, what can I raise 2 to the x to equal 4? Well, I hope you're telling me x is 2. What does that mean? Don't make them guess what that means. Write out what that means. It means the reaction is second order with respect to A. So now I know y was 1 and x is now 2. I know a lot about the orders of my equation. So this is what we know so far. Now I do want to point this out. Why did we not compare equations 2 and 3? So let's take a look at that. 2 and 3, what happens to A? Well, A doubles. What happens to B? B halves. What happens to C? C doubles. Could you have worked with this? Well, yeah, you could. Would it become a mathematical nightmare to ask you 2 to the x times 1/2 to the y equals 2? Okay, and then y, we already know is a 1. Okay, so 2 to the x times another 1/2 equals 2. How are you going to work that out? Okay, yeah, it can be done. Is it going to be more difficult and take longer? Absolutely. And there have been times on the AP test, I'm not expecting this anytime soon, but there was a year on the AP test, one of these exponents was a fraction. Now you can imagine how much that would throw a wrench into things. So I do not expect that. I expect it to be like we've seen earlier, but choose wisely. If you don't have to mess with a 2 to the x times 1/2 equals 2 bit, don't. Pick wisely from your chart where one thing is held constant and one thing changes, or at the very least one thing changes and everything else is constant, and you see what effect that has on the rate. And that's good science. That's good isolating your variables. Okay. With that said, here's our rate equation so far. We want to know how we can determine K, the rate constant. So I have that exponent, I have that exponent, it's a 1. We're just not going to write it. How can I solve for K? Well, to solve for K, I would need to know a rate, I would need to know a concentration of A, and I would need to know a concentration of B. I would need to know a rate, a concentration of B, and a constant. Oh, we have the information in the chart. We could pick an experiment and we could plug in those numbers to our rate law, and everything would be plugged in except for K, and then we'd solve for K. So let's do that. Which one? It doesn't matter. Okay, between you and me, you could pick 1, 2, and 3. I just like picking 1 all the time. That's just me. That's what I do. Okay. So you're going to pick experiment 1. Now you need to tell them. You listen to me. On the AP test, take 5 seconds to tell them which experiment you're going to use. And I've even seen students, and I've been told they take this, like circle the 1 and draw an arrow down and show they're using data from 1, and they said that works too. What does not work is to not indicate at all what experiment you're using. So indicate it. So here's my formula. They like to see the formula. Check, got the formula. Here's my numbers plugged in from experiment 1. Check, and I told them what experiment it was from, so double check. And then I algebraically solve for K. Okay, does this show you know math and calculator skills? Yeah. But you know what, it's minute. It still shows you know a lot of chemistry. This was chemistry, this was chemistry, this was chemistry. This is the only, non-chemistry parts. So that's not bad. Now I want to show you this. I have had the labels here from the chart. Over here actually, sorry. So that label goes there on that number. Okay. I have this label here. What happens when I have molarity and it's to the second power? Well, that becomes molarity squared. So not only am I squaring that number, I'm squaring that molarity as a label. What happens when I have molarity to the first power? Well, that's molarity 1. What do I do when I multiply labels? Well, you know, x squared times x, or m squared times m in this case, is m cubed. So there's my m cubed from this side, and then there's that label from that side going on there. What reduces? Well, that m will reduce that to a 2. So I have a per second going on still, and I have two molarities that have a molarity squared that has not canceled, and it's in the denominator. So I'm writing it that way. In other words, what am I writing? I'm writing 1.5, because I calculate that out, and it's 1.5, divided by molarity divided by seconds. Oh, sorry, molarity squared divided by seconds, because negative exponents are fractions. You can write it either way. They will not carry on the AP test, because they're mathematically equivalent. So K's label is per molarity squared per second. So what determines the label for K? It is the orders that determine the labels for K. So you use your chart, use your orders, and you see what cancels and what doesn't cancel. And if you're not in the habit of showing your labels when you do your work, that's just stupid. The labels are there to keep you straight, and especially when you're dealing with lowercase k, the labels will tell you what the right label is for lowercase k. How you could get through thermodynamics without matching joules to kilojoules, you couldn't. But you wouldn't know you have one number in kilojoules and one number in joules if you weren't using your labels all the time. You wouldn't know that your temperature in Kelvin and your temperature in Celsius don't match if you didn't have the label there all the time to let you know, hey, they don't match, let's convert. So please, 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 for your own sake, always use the labels. I know it's a hassle, but it's like a 2-second hassle. It is worth it for the results. Especially with this, there's no way to memorize the label for K. What's the label for delta G? Probably kilojoules or joules. What's the label for delta H? Probably kilojoules or joules. What's the label for delta S? Probably kilojoules or joules per Kelvin. You can memorize that much, okay? Can you memorize the label for K? No, not at all. Can't be done. It's your labels in your equation that would show you your label for K. All right, so what do we know so far? Now we know this. And as I've already discussed, what's the other way to write the label for K? You could write it as a fraction. So we could have said rate is equal to 1.5 over molarity squared per second, per molarity squared per second, times concentration of A squared concentration B. This is what we call our rate law for this reaction. Now I want to point out the coefficient in front of A is a 1, and that's a 2, and the coefficient in front of B is a 2, and that's a 1. No connection. Don't try to make a connection there. There's no connection there. Please don't try to connect them. Okay, let's do another example. Oh dear, what do we have going on here? Well, we have an A, B, and C going on here. What's that mean? Well, that means while I try to look for A, I want to hold B and C the same. And while I try to look for B, I want to hold A and C the same. And while I try to look for C. So it really is not harder. It's longer, but it's not harder. Okay, so what's our general rate law form? And I'm going to switch to a darker color. We're going to have that rate equals K concentration of A to X, and I just pick X. Concentration B to the Y, concentration of C to the Z. I just picked XYZ to pick XYZ. It doesn't have to be anything in particular. It most definitely has to be an ABC because that's what they're using here, and that's what they're using here. And if they used elements and compounds instead of A, B, and C, you better use elements and compounds and not just A, B, C. Please use what they give you. That's part of the good communication skills that you are trying to develop this year. Okay, so there's our general rate law form. Now that we know that, what's the order with respect to A? So I want A to change, and I want B to stay the same, and I want C to stay the same. So where does B stay the same? Where does C stay the same? Hey, that works well there. So I'm going to say between experiments 2 and 3, what happens? Concentration of A. Okay. Oh, we're going to get into like a half thing. Do we want to really work with a half? Here's a little chemistry trick. Let's not say that. Let's say between experiments 3 and 2. And you're like, well, what difference does that make? Well, check this out. Now I'm going this direction with my arrow, so the concentration of A doubles instead of halves. It makes it easier to work with. I don't need a fraction in my math. The concentration of B stays the same, and the concentration of C stays the same. The rate, now remember, I'm going this direction now. So whatever direction you go here, you have to go over here. Be sure you're going the same direction all the time. Okay. Since exponent's the same, I'm going to look at that. And that is the rate increases by 4. Now you can say the rate quadruples. They'll take that. That's fine. I just don't like trying to write the word quadruples. It doesn't work well in my dyslexic head. So I like to say the rate increases by 4. Now let's do the math. Okay. A doubled, so that's 2. And A's exponent was x. B stays the same, and so that's 1. And its exponent, I'll throw that in there just for kicks. And C stayed the same. And the rate went up by 4. Now, 1 to any power is still 1, and 1 to any power here is still 1. So these ones are gone. You don't necessarily need to scribble them out. I'm just showing you how to focus on what's important. What's important is here. Therefore, x equals 2. The reaction is second order with respect to A. And you could say concentration of A there. Same thing. Okay. So now I know what A is. Okay, let's do it with respect to B. While I change B, I want to keep A and C the same. Okay, well, we have some choices here. Okay, so A stays the same in 1, 3, and 4. And C stays the same in 1, 3, and 2. So let's pick these two and these two. Does B change? Yes, B does change. So, in experiments 1 and 3, concentration of A stays the same. Concentration of B increases by 1.5. I know that's weird, okay? But don't worry, it's going to work out in the end. We can handle this math. And I'm going in this direction, so I'm looking still this way. So concentration of C stays the same. And the rate, now I was going from 1 to 3, 1 to 3, 1 to 3. I want to go 1 to 3. Exponents are the same, so look at the numbers, and the rate stays the same. So, what would this look like mathematically? A stays the same, so that's a 1. And we know A is second order, so if we wanted to put that in there, we could put a little 2 there. But it makes no difference because 1 times 1 squared is still 1. B increases by 1.5. C stays the same and the rate stays the same. Well, this is interesting. We're looking for y. Okay, z here. This doesn't really matter. This doesn't really matter. What can I raise 1.5 to equal 1? Did you catch that it's zero order? Because anything raised to the 0 is a 1. That's why you actually learned that in mathematics. I know at the time you're like, I don't know why we need to know this. This is why we need to know this for rate loss. Okay, so y equals 0. So what do we know? The reaction is 0 order with respect to, well, not y, sorry, respect to concentration of B. Okay, and if you're really regretting my bad handwriting, just know that that's mostly due to the fact that I'm using a stylus on my screen and it's not picking up all the nuances of my writing. On the AP test, I would take the extra like 10 seconds per answer to be sure I'm writing clearly. They would do their best to read this. I just would not want to make it hard on them. If you are their last test they are grading, at the end of the 7th day in a row of test grading, anything you can do to make your test easier to grade is going to work in your favor. Okay, I mean, they'll try their best, they really will, but it is usually going to go better for you if you make it easier on them. Okay, so A was second order, B we now figured out was 0 order, C, let's figure out what C is. Okay, so I need some experiments. In experiment, let's see what's going on. A stays the same in 1, 3, and 4. B stays the same in 2 and 3. C stays the same, or C changes in any of them going to 4. So what do I want to pick? We obviously want to pick something where C changes. So I'm going to end up picking 4. Can I pick a 4 where B stays the same and A stays the same? No, I really can't. Is this a problem? It actually is not a problem. Okay, we have some choices here. I'm going to go with 1 and 4, and you'll see why I picked that in particular. But let me point this out. A stays the same, B doubles, and C triples. And then we have our rate changing over here. Okay, so in experiments 1 and 4, concentration of A stays the same. Concentration of B doubles. And concentration of C triples. And the rate, now let's check out the rate. Exponents are the same, so look at the numbers. The rate triples. Now let's look at the math. A stays the same, so A is a 1, and we've already determined previously the order of A is second order. B doubles, so we're going to put in a 2 there, but what did we previously determine is the order for B? Oh, we determined it 0. That's going to be useful. And then C triples, and I'm looking for Z, and I want to know if the rate triples. So anything, no matter what the exponent of 1 is, that's still 1, so that just kind of disappears, it's gone. Anything to the 0 is a 1, so that kind of disappears, that's gone. So still, even though we could not isolate A and B staying the same and only change C, once I knew B, I was able to still just use that in my equation, and I'm okay with that. It works. And now we ask, what can Z be to make 3 equal to 3? And we say, therefore, Z equals 1. So the reaction is first order with respect to concentration of C. All right, we have A, B, and C. Now let's find value of K. Ooh, this is fun. No big deal. Okay. So rate equals K, concentration of A to the X, concentration B to the Y, concentration of C to the Z. Let's plug in what we know so far. We know the rate is equal to K times concentration of A to the double, okay, squared, second order is how we would say that. I want you understanding the vocabulary. A is second order. B, we've already discovered is zero order. And C, we just discovered is first order. Now I'm ready to plug in and solve for the rate, and I like to use experiment 1 because that's just the way I roll. So from experiment 1, my rate, 2.4 times 10 to the negative 6 molarity per minute is equal to K times the concentration of A is 0.20 molarity squared. B, I don't have to worry about it, zero order. And C, concentration 0.20 molarity to the first order. Okay, so let's solve for K. So K is 2.4 times 10 to the negative 6 molarity per minute divided by, okay, so let's square that. That's 0.040 molarity squared times 0.20 molarity. Okay, no, sorry. And now we are ready for a calculator. And on the bottom, when I have the 0.04 times 0.02, I get 2.4 times 10 to the negative 6 molarity per minute is going to be divided by 8 times 10 to the negative, and you could leave it as a decimal, that's fine too. 10 to the minus 4 molarity to the cubed, molarity cubed. Okay, when I do this math, 2.4 times 10 to the negative 6 it would help if I could find the negative button. There we go. Divided by 8 times 10 to the negative 4. And I get 3.0 times 10 to the negative 3, which does not surprise me. 24 divided by 8 is a 3. Look at that approximation. 6 minus 4 would be a 2, negative 2. However, I'd have to move that decimal one more place, so that's why it's negative 3. Having some good number sense helps, just knowing you're on the right trail. What's my label? Super important. That molarity will cancel one of those molarities, so I get per molarity squared per minute. Okay, let me do that better. Per minute. There we go. There we go. So there's my label. There's my value of K. 3.0 times 10 to the negative 3. So what is our rate law? Here's our official rate law. Rate equals 3.0 times 10 to the negative 3. And you could write that on decimal. Per molarity squared per minute times concentration of A to the second order, concentration of B to the zero order, and you could skip writing that, they'd be okay with that, times concentration of C to the first order. And that is our rate law for that reaction. Okay, so I've walked you through a rather simple example and a rather not simple example. I mean, it really doesn't get much harder than that. We can talk about this case where we say, well, what if we want to know the time it takes to do things? And that's a very important topic. So we're going back to like experimental data, wrong way. And we're like, okay, so if I'm starting with 0.2 molarity, how long would it take to reach 0.1 molarity? Or how long would, or over here and over there? So having the rate law, where we have the rate, is the first step in figuring out how long will it take for this much concentration to be left, or this much concentration to be used up, or however you wish to view that. So we now have, with our rate law, which takes a bit of time to develop, we have a lot of useful application for it. Now those applications I will give you examples of in the next video. I want to stop here for this video, and you need to practice doing this technique. Okay, but this is, again, with a rather simple previous example and now a rather not so simple example. You see how to do it. If you pick your experiments wisely, it almost always works out with minimal math needed. I do want to warn you, once again, if they use A's, use A's. If they don't use A's, if they use, say, I don't know, hydrogen peroxide and hydrogen peroxide, then use hydrogen peroxide. Okay, please don't suddenly pick A's. If you're picking something they don't give you, they're going to wonder, where in the world is your mind? And you are not going to get your points. So be careful about that. All right, so good luck on this assignment, and I will be talking to you again soon.